All right, so I think we're recording. I hope you can hear me. Good morning, good morning. This is our first week of the weekly review for statics. Um, so I'm going to be doing this every week, and I guess how I'm going to structure these weekly reviews is I'm just going to be picking problems out of the book, and the book I'm using is Engineering Mechanics. Statics and Dynamics. So this is the book I'll be working out of statics and dynamics. Yeah. So this is the book I'll be working out of. I'll just be picking problems out of chapter 2 this week. So this week and we went over chapter 2. So I'll just be picking a few random problems out of there and just kind of working through them. Um, making sure you kind of have a good understanding of how the math works. So chapter 2 goes over, let's see, forces and force vectors. And force vectors. All right, well, let's go ahead and get right into a problem then. So also, if you want to contact me to ask me about specific problems to do, you can message me on Teams. My name is Ashton. Message me on Teams, and I'll let you know what kind of problems you want to see. So, kind of diving right into it then. I'm going to start off with problem 2-4. So let's go to the book here. I'm going to start with problem 2-4. And this is what the picture looks like. Hopefully I can draw it good. There's a wall there. It's a pin in here, something like this. All right, call this A, B, C. And we're also saying that this right here, this angle is 45. And this angle here is 30. All right. So the question says, if you have this pulled up in the book, it says the vertical force F, there's a vertical force here, a different color. Vertical force F downwards. On a two-member frame, determine the magnitudes of the components of F directly along the AB and the AC. So we want to find what's the force projection of F on these axes I'm drawing in yellow here. All right. And let's go ahead and set F to 500. 500. All right, so if you remember from chapter 4, we talked about projecting F onto certain axes to get it into, break it into components. So how we're gonna approach this is we want to analyze the triangle that's being made here. So there's two forces. There's a force directed along here. All right, and there's a force directed along here. You can see this is force AC, force that's on AC. There we go. And this other one is force AB. All right. Okay, so now we kind of want to analyze. We know these two forces here, AB and AC, should add up to sum to this 500. And so we can make this a parallelogram, right, using the parallelogram method. So this makes a parallelogram like this. I'm gonna draw it a bit bigger over here, but we're looking at that shape right there. So I'm gonna draw it like this. Where, you know, this over here, straight down. Okay, there we go. So this here is our F. This here is 45 degrees, right? They give us that in the problem, and what else did they tell us? They told us this over here is 30, right? This over here is 30. Right, so basically I just took this over here, this over here, just kind of expanded so we can see it a little better. And so we know this is 45 and this is 30. If you kind of look at this angle, you can see how it relates to this angle out here. So if I draw another parallel line, right here. All right, make it black. Look at this line and kind of look at this line. That's how we know that this angle is 30. So this angle over here must be 30, right? So that's kind of what I'm showing here. This is 30. Okay, so far so good. So now you kind of, we can basically want to analyze these triangles so we can either use the law of cosines or the law of sines. So we know this is 30. So this is 30, this is 45. Then this is 45, this is 45. We can actually solve for what this little piece is. This is a right angle, so that must be 60. Let's write that in the color. This must be 60, right? So all this over here is going to be what, 105. In other words, you could say this over here is 60. And over here is 45. Well, that means we can solve for this last side over here, this last angle. And so from here, we kind of see we're going to end up using the law of sines, which is this sine alpha sine beta and sine gamma, right? So let's call, F. So F here is going to go with this angle I have in red. So F goes with this angle over here, which if we do the math, this triangle should sum to 180. This is 105, so that makes this over here, what's that, 75, right? Okay, so from there we can basically use the fact that we know both of those to solve for the other two sides. So this F, let me write all this out now and try to color coordinate it. So this over here was FAB. That basically goes with the angle 60 over here. And then this, or you can kind of imagine it over here. That's our AC, FAC in blue, so it goes with 45, right? All right, so we can kind of see what goes to where. So now using our law of sines, F is 500, this is 500 over sine of 75, right? equal to FAB, which is the orange one. So it's going to be over sine, let's call it beta, or 60. Which equals FAC. Okay, speeding up here a little bit now. So that's going to be sine of what's the red one, right? With 45. All right. Okay, so from here, I'm just going to kind of leave it at that because we see that using force 500s, this force here given, and the angle on 75, we could solve for FAB and FAC, which is the force along that, along these the axis of AC and AB. Right, so we just multiply sine 60 over, solve for FB. So I write that out. So FAB is going to be sine 60 over sine 75 times 500. This one's going to be FAC is going to be sine 45 over sine of what, 60, or no, over 75, right? Hope you can write my handwriting. 500. Right there. Okay, so that would give us our answer there. So this is problem 2.4. So I wrote that down. In the statics and dynamics book, 2-4. Okay, so basically here, takeaway is how we use the law of sines and how we projected this vector here onto the AAC and AB axis and kind of analyze those forces using the parallelogram method. We make this parallelogram here and analyze the triangles inside. All right, so let's do another one. Let's do another one. Let's do 2-8 now. Yeah, let's do 2-8. 2-8. So I'm going to draw the picture first, and I'll go from there with something like this. Yeah, this is F1, and let's make it 6. And this is F2. Okay, and they give us this coordinate system. Right, but this here is B. You can see that yellow, and this here is here. Where U and V are not necessarily perpendicular to each other, like the X and the Y axis are. So just kind of keep that in mind, like that V and U are not always necessarily perpendicular. Meaning, like for this problem, they tell us that they give us this angle here, they give us this angle, it's 30, and this angle here is 30. And what else? They tell us actually the angle between those. This whole angle here is 75. All right, not bad. Okay, so the question says resolve force 2. So resolve force 2 into components acting along the U and V axes and determine the magnitude of the components. Okay, so I'll write that down. So we're going to resolve into components. See that? Yeah, okay. Okay, so we're going to resolve F2 into components, and of course along the B and the U here. Let's pull up that note. Okay, so let's analyze what's going on here in this picture and use a different color. So we're going to resolve F2 into components, right? So first, just kind of looking at the picture. You know, this here is 75, so we know this angle in between here. So this is 60, 30 plus 30, 60, minus 75, 15. So this here is 15. This angle here is 15. Okay. So what's that mean for, it's this angle here? And so let's also draw the projections. So we have this projection right here. All right, that's F2 on the U, right like that. And then we have this projection over here. That's F2 on the V, right like that. Okay. Okay, so I wonder if we can solve for what this side's going to be. I think we can, right? Because this, you could say this whole thing is a circle, so all these angles should add up to 360. Let's see. We know this here is 75, so this over here. Oh wait. Let's see that on the picture. Yeah, actually the picture right. Okay. So this isn't actually 15. That's a mistake. Let's see if I can erase that. It's not 15, right? It's this whole part is 75, not all this, right? And so it's 75 minus 30. So it's write that down. So this is 45. That makes more sense. All right, thanks for catching me. So yeah, that makes more sense. So it's 45, that's 30. So this over here must be, but I'll say this is 175, this is 75. Then these two halves, let's write it. So this thing over here and this thing over here is what I'm kind of looking for. So 75, right, plus 75. That's for these two. That's for, that. That's for the two outside angles. Okay, so subtract that from 360. I'm going to divide that by 2. So 360 60 minus, what's that, 150? I think this is 105. Yeah, so that gives us 105. So this green angle is 105. So this here is 105. So all that just to kind of find out that this angle here, so say this here, is going to be 105 minus 30. That gives us, what, 75 again? Yeah, it's 75. Okay, so now kind of the bulk of the work is done. So really the whole thing was just kind of analyzing what's going on here. So starting off knowing that the U and the P are not perpendicular. They have this angle of 75 between them. So this is 75. All this is 75. Then using that, we were able to solve this outer angle of 105. So then we can solve for this 75. All right. Okay, so now let's do our law of, I think this is going to be law of sines again. Let's write that out. So we got A sine alpha, B sine beta. All right, can you kind of see what angle we're going to look at? So we're going to look at this one, right? Because we know everything about this angle now. We know that this is 75, so this is 30. I think over here is 75, and down here is 30. All right. So then over here is also 75. And then down here is 30. Yeah. Okay. So now just kind of make sure that's right. Does it make sense, right? Yeah, because if this is 30 and over here is 30, yeah, 30, 75, this has to be 75 because it has to add up to 180. And that does. Okay. So let's be more clear about what's what now. So this over here goes with 30. So F2 be sine 30. All right, let's equals, switch colors. If you're looking at this red, right, that's basically this side over here. All right, that's F2U. So F2U. Excuse my handwriting. Let's see, what's that one gonna go? Well, it doesn't matter. The last two go with 75, right? But it's this one over here. And then what's this one? This one. Okay. And finally, just put all that in. So sine 75, 75, F2 over sine 75. Okay. Did they give us what F was in the problem? Let me see. They did. They said F, well, F2, I mean, F2 is equal to 6 kilonewtons. Okay, so knowing that, we can just plug that in there. That's 6 kilonewtons. Put that in there, and then we can solve for F2V and F2U. Okay, so this is similar to the one before, right? We just made this parallelogram with F2 and kind of analyze the angles to get the components. Okay, so in the end, we're going to have F2U equals, well, if we kind of look at it, it's an interesting result. It's sine 75 over sine 75. So those two cancel out. Times 6. So F2 is equal 6, and F2V, let's see, it's going to be sine 30 on the top over, let's see, sine 75 times 6. Okay, and those give you your answers in kilonewtons. All right, not bad. So again, the whole idea is just analyzing these triangles using the parallelogram method and using those angles to use the law of sines to solve for the components. All right, let's see. So I think all that goes over the first section of chapter 2. Let's do one that uses the law of cosine. So let's do number 10 actually. Yeah. And then I'll move on to the next section, just so you can kind of see another equation that was introduced in chapter 2, which looks like this. I'll just write it down first. It's the law of cosines. Right, with this kind of idea in mind of a triangle that looks like this, where this is alpha, gamma, gamma, beta, as we say, C equals the square root of a squared plus b squared minus 2ab cosine of gamma. Well, yeah, gamma. Right? So that's the law of sines there. So let's apply that to a problem, and we're going to do problem 2 to 10. And then I'm going to, what time it is? Almost 30 minutes, yeah. So this is 2-10. Okay, so 2-10 basically looks like this. What they give us, this is the y, this is the x, and there's a force this way, and this is 40. This force has a force of 800, and there's another force down here. They're basically two ropes, but I'm not drawing the ropes, I'm just drawing the vector. So I've got these two forces here pulling outwards. This force is 500. This angle is 35. And the question is, determine the magnitude of the resultant force. So I guess I'll just call this one 1, this one 2. So we want to find magnitude of the resultant force, Fr. All right, and what else do we want us to find? And find its direction measured counterclockwise, so find, so let's call it theta. But theta is the angle of the resultant force. So using again a parallelogram method, because we're adding these two vectors up, F1 and F2, we're plus F2 using a parallelogram method to draw out how that'll look. Draw this red line that's parallel to F2. Draw another line that's parallel to F1. And then starting from the center here, I'm going to the other end is the resultant force. Right? Okay, so we want to find the magnitude of this resultant force and what else? And the angle. And I'll also note that these are magnitudes. I'm going to find the magnitude of that force too. Okay. Okay, so let's kind of analyze this again, this parallelogram, and see what we can find out about these angles. Because we already know, well, kind of as I've alluded to, we're going to use this method here, the law of cosines. And so kind of looking at this, we see we know this side, and we also know this side, where, color, know what this side is, and we know what this side is. And we're trying to find this red side. Okay, so it'd be nice if we knew what this angle over here was, this angle opposite to it, because that's kind of how the law of cosine works. Notice that it uses the angle opposite to whatever side. Okay, so how do we figure out what that is? So instantly we can say, well, let me change colors here. It's kind of like that's 35. So if I were to draw another kind of, let's see, this goes like this, so it goes out like that. This goes like that, like that. Yeah. Wait, what is that again? It's supposed to be 40. This is supposed to be a 40. Okay. So if we add up 40 and 35, that gives us, what, 75? Well, that gives us actually, yeah, 75. So this is going to be, I think, 95. All right, 95 plus 95 is, oh, actually, we can solve for what this angle is, right? This is 40, then this must be 60 right here. Right here, right? That angle was 60. Okay. Well, that tells us that this whole side is 60 plus 35. So 60 plus 35 is at 95. So this whole thing is 95. So then that's how I got this here to be 95, where I could put it up in this end. So right here is 95. Right? I hope you saw how I got that. All I did was note, because we know the x and y are perpendicular. Note this force measured from the y is 40. So to be measured down to the x must be 60. Well, actually, not. It should be 30, right? And that one should be 30. And it should be 50, excuse me. that should be 50. Right, it has to add up to 90, this whole thing. So yeah, that was our 40. So that's 50. All right. Same idea though. So now 50 then plus 35, that's 85. Yeah, so this whole thing is 85. So 85 plus 85, I'm gonna do this again, 360 minus 2 times 85, and I'm gonna divide that by 2. So 60, 70 is 360 minus 170, divide that by 2. And so basically what I'm doing is I'm trying to solve for what this side is. So again, this whole thing, 85 plus 85. So subtract that, that's 170, 360 minus 170. So we got 109 over 190 actually, over 2, 190. Okay, so there we go, that gets us to our 95. So that's how that's 95, right? All right, so that kind of comes to the final part now. So again, we're trying to solve this red side. I'm going to use the law of cosines. So just kind of plugging in the numbers. So it's going to be equal to the square root of 500 squared plus 800 squared minus 2 times 500 times 800. Cosine of 95. Okay, so that gives us the magnitude of f. Let's talk about that. F resultant. Okay, so same idea. We have this parallelogram that we have to analyze some kind of way, right? And by analyzing parallelogram, we can either use the law of cosines or sines. This time we use the law of cosines. So we still want to find the angle. So that angle, we're trying to find theta. Theta is this angle here. This is theta. All right. And this whole thing from here to there is 50. All right, so you kind of see the difference there. Okay, so I think to find this, now this theta, I think we would have to use the law of sines actually. Yes. Okay, so solve for that theta. Well, actually, solve for this angle over here. Excuse me. Let's call it a different angle. Solve for this over here first. Right? Let's call it psi. If we can solve for psi first, and I'm choosing this angle up here, psi, because it goes with the triangle that's being made here. So I think we can quickly solve for psi using the law of sines. Then we can say psi goes with 500. So say 500 over sine of psi. So it's equal to, let's pick 800, right? 800. And let's see, 800 goes with, oh, here's 800. 800 goes with this angle over here. All of that goes with this angle. And that should be what? That should be 35, right? Yeah. And I know it's 35 because it's the same as this angle over here. This is 35. Actually, better yet, I don't think we know that side, but better yet, we can use, I don't think that's 35. I think better yet, we can just use this side. No, it's 95. So instead of using that, we can just use the resultant force in 95. That looks better. Because we would have solved for the resultant force first. Once we kind of had that number, we can plug it in here to solve for psi, right? And then solving for psi, we can then solve for theta, because I guess I'll just write this last part out, kind of leave the rest up to you if you want, and say theta plus psi should be equal to 50, right? Because they're right there within 50. Okay, so let's move on to the next one. So I think that does enough for the law of sines and cosines. You kind of get the idea of just you got to analyze the parallelogram. Be careful with the angles. You really have to see what angles what. Try to make sure that triangles add to 180. Make sure squares add up to 360. Okay, so let's move on to the next section. I want to do such get to 10. So let's skip down to the next section. Okay, let's do 2. Skip down pretty far. Still like 41. Yeah. Even 241 is okay. Has multiple forces, so let's do 241. 2 dash. Okay, so I'm trying to do this one a little faster. So we got x and y axis. We got 3 forces acting on the origin here. A force this way. We have a force this way. We have a force this way. We call this one 3. It has a value of 8 kilonewtons. This one's 2 and it has a value of 5 kilonewtons. This down here is 4 kilonewtons. Okay. And it says determine the magnitude of the resultant force and its direction measured from the. So basically, we want to find the magnitude of the resultant. This is it, right? And theta. Boom. So we know the resultant force is going to be the sum of F1 plus F2, F2 plus F3. Right, so that basically means we have to add up its components. Yeah. So 3 forces going to add up their components. And oh yeah, they give us these angles. So yeah, of course they got to give us the angles. So they give us this angle here, 60. This angle here is 60. They give us this one here is 45. Okay, so there's a lot we can figure out from there now. So now in this part of the section or of the book, before we found the components using the angles, now we're gonna still break down the forces in terms of their components, but we're gonna add them up differently. We're gonna add them up with the components versus using the angles, if that makes sense. So basically what I mean is each one of these forces has an X and a Y. This has an X and a Y, and this has an X and a Y. So I'm gonna write each one of them out over here on the side. F1, this just has an X component. I, or force 1 just has an X component, right? And so force 2 has an X component that we can write this way, write it as 5 cosine of 45, right? That's the X component. Well, and it has a Y component, right? So 5 sine 45 J to 5. That's a 5 plus here, right? Basically, I got those from projecting the force 2 that was right here. So that right there is force 2, but the J component, so I can write it like J. Or X component, excuse me. And this one is F2, X component. Right. So was able to solve for those using this angle, right, of 45. All right, I think that makes sense. And lastly, there's F3. Okay, so F3 is a little different with the angle that they give us, right? But I think we can still solve for what that is, because it should just be, let's see. Let's see, it's F2, it's F3. Let's add up, actually. 60 and 45 add up to 105. So this over here, let's see if this helps. This over here, that's 105. 180 from 105. That's 75. So if that's 75, then this right here must be 15. There we go. All right. This here is 15 because 15 plus 75 gives us 90. And this is 75 because 75 plus 60 plus 40 is 180. Okay, all that checks out. So now we can use this angle of 15 to write a projection for force 3. All right, kind of looking at this triangle that's been here. And so F3 is going to have a negative A. It's going to be the sine component. It's going to be sine 15. It's going to be the I hat plus B cosine 15. You can see that yellow. So minus 8 sine 15 plus 8 cosine 15. And again, I should put the J hat with that too. And so again, the cosine is now with the component because we're losing this angle of 15, and the opposite over here is the J component, or it's actually the X component. Excuse me, I'm mixing my words up. It's the X component. So see how that relates with the opposite side, so it's sine. So that's why it's sine, and it's negative because its projection is pointing in the negative direction. All right, it's going in this direction here. All right, that force is going in the negative X direction. That's how we pick up that negative there. That's kind of key. All right. Okay, so now this is the easiest part. Now we can just add these up. Yeah, so now we add them up, right? And that gives us the magnitude. I guess I'll write it like this. This is 4 plus 5 cosine 45 minus 8 sine 15. Close parenthesis, all that is the I hat plus, let's see, that's 0 plus 5 sine plus 5 sine 45, and what else? Plus 8 cosine 15, all that J hat. Okay, so finally now we have, this is the resultant force. It's X and Y component. So we want to find the magnitude, right? So I haven't done any calculations yet, but we know that to find the magnitude, we can't just take the square of the components. So FR X component, right? Squared plus FR Y component squared. Square root of that. Okay, so now that gets us our magnitude. And if you put that in your calculator, I think you should get something like this. You should get about 12.5 kilonewtons. Okay, so once you put all these numbers into this, you should get 12.5. And now for theta, theta is a bit easier to solve for here because we have an equation for theta. Well, theta is going to be equal to the arctangent, right, of the y components over the x components. So again, I haven't put in the numbers, but you kind of imagine that would solve for that, would solve for this, plug both of those into here, and get our angle to be 64. 64.1, 64.1, I think. Okay. So I guess that's kind of the gist of the next section of the chapter 2, right? And so now we're adding up forces using their components. And before we were adding up forces kind of by, it was only two forces, and we're able to analyze the angle to solve for the resultant force or any of them using law of sines and cosines. Whereas this one, we use sine and cosine to determine the component. Now, if it's two or more vectors, you're gonna wanna basically have to do it this way, where take these vectors and break them down. But if there's just two vectors, then you can use the parallelogram way or the force component method. It just kind of depends which one you're more comfortable with. Okay, let's jump a bit further now. But so far, we've only talked about the law of sines, law of cosines, and how we break that forces into components. Excuse me. So let's go down. This looks like a fun one. Let's do. Yeah, let's actually do 272. There's a star on it. Not exactly sure what that means. It's special. Right. Okay, so 272. So now we're in 3 dimensions. Before, up till now, we've just been in 2 dimensions. So now we're in 3 dimensions. We're always going to use this kind of right-handed coordinate system. That's what they call this. It's right-handed coordinate system. And there's two forces, right, from the origin. It's a force this way. Call it force 1 equals 80 pounds. And there's another force. Another force. We don't actually know where it's like directed or anything, but they do kind of draw it for us this way. Okay. And that's force 2. We have no information about that. And then there's the resultant force, which comes from the addition of those two forces. Let's draw that in blue. All right. Using our parallelogram method here. There's our resultant force. It has a magnitude of 150. All right. And they tell us the directional angles of the resultant force. So in the previous chapter, we talked about directional angles, which are basically just angles that describe a vector in 3 dimensions. So from the x-axis, all the way to that resultant force, we call that alpha is equal to 120. That's a directional angle. It's 120. Yeah, excuse me, later numbers there. And what else? It looks like they give us this angle. What's this angle here? It's 130. And that's going to be our beta. And lastly, they don't give us gamma, which I guess goes from the z-axis down here. All right. So that's the picture they give us. The question is two forces, F1 and F2, act on the origin here. If the resultant force has a magnitude of 1, start figuring out there, 150 pounds, and they show us these directional angles, find the magnitude of F2. find the magnitude of F2 and its directional angles. So let's call it alpha 2. Excuse me. Okay, yeah, alpha 2, beta 2, and gamma 2. Okay. So first of all, you know F1 and F2 sum up to be the resultant force, right? And so you have this, obviously, right? Force 1 plus force 2. So now, since we have the directional angles of the resultant vector, we can write this x, y, and z components in terms of the directional angles, right? By using this over here, I'll write it over here. Because we can say cosine alpha is equal to, I just call some vector A, x component over the magnitude, gamma, I should do beta, so I can see beta. So that's supposed to be gamma. And cosine gamma AC. Pretty nice, right? Okay, so using those directional angles, we can write the resultant force in terms of x, y, and z component. Okay, and we can actually write out force 1, right? It's only in the y-axis, so we can write out its components too. Okay, so we should have a way to solve for F2. Let's put all this in. Because we're going to have 3 equations, right? Right here. So we have the magnitude of the resultant force, which is 150 times cosine alpha equals F1x plus F2x beta F1y plus F2y, right? Fr cosine gamma. Get the idea, right? So, because basically all this over here is the resultant force, right? All that right there is the resultant force. Then this is F1c plus F2c. All right, then all this right here is basically just F1 plus F2. Right? So we have 3 equations there because we're in 3 dimensions. So we know what all this is, know all this information, or except actually we don't know this gamma, that gamma there, but we can easily solve for that by using this cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1 using this identity here. You know, you can instantly see how we can solve for gamma because we know alpha and beta. So gamma looks something like this. Square root, more than just the square root. It's going to be the inverse. Yeah, inverse cosine, close parenthesis. Now square root of 1 minus, right, cosine alpha minus cosine squared beta. Close parenthesis there. All that's under the square root. Right, subtract them over, take the square root, and then do inverse cosine. Okay, so if we do that real quick in our calculator, we can solve for gamma. They don't give it to us, so let's see, gamma. So I think after doing that, we get gamma to be about 74.52. Okay, so we solve for gamma now. So with gamma, we can now go over here and say, well, we can plug in gamma here for, now we use all three of these equations to solve for, well, I guess we want the components of f, right? So we want to solve for all of this over here. And so here, I'm going to just write out what that's going to be. These x components for force, these components for force 1. If you look at force 1, it only has, it's on the y-axis, so it only has a y component. So this right here is this is 0. This part right here is 0. This here is 0. This here is 8. All right. Okay. We're running out of room. But I got a little bit more room to write the answer. So now kind of using this, we can solve for all those components. So we'll say f2x equals, I'll just put the numbers in. So we have 150 cosine of alpha, which is 130. Oh no, alpha is 120. Okay. Force 2y is going to be, real quick here, 150 cosine of beta, which is 130, minus 8. F2z is just going to be 150 cosine gamma, which is 72, or 54, excuse me, 54.52. Okay, boom. So now those three components of the force 2. Okay, so now I'm still can find the magnitude. All right, whenever we want to find the magnitude of something, we square each one of the components and add them up, take the square root over all over the top. So F2 is going to be equal to square root of, well, get the idea, right? Kind of out of room. You'll take each one of these, square them, then put it under this square root here. Okay. So lastly, before I move on to the next problem, oh yeah, because we still have to find alpha, beta, and gamma, which are the directional angles for F2. So I'm actually just going to clear all this. Yeah. Okay, so again, we're doing number 72. We're in basically the home stretch of it now. This is F2. This here is F1. We added those up. It gave us this resultant vector over here. And then we know what these directional angles are. This one, this one, this one, alpha, beta, gamma, Z. So I just kind of show real quickly. We can use the directional angles for any vector in 3 dimensions. So we can also use directional angles for force 2, and kind of the same condition would apply. Cosine alpha, I'll call it alpha 2, right? Where alpha 2 is going to be like this, alpha 2. It's going to be equal to the F2 x component divided by the magnitude. Alright, so I'll speed up here now because it's going to all follow that pattern. Boom, right? So we can use now these, because we've already solved for the x, y, and z component of 2. We've just solved for the magnitude of 2, right, by taking the square root of those components. And now by just doing inverse cosine, right, inverse cosine, -1 equals alpha 2, so on and so on. Okay, so I'm gonna leave it at that. So let's go to another problem in. So that was problem 217. We used directional angles, and just everything that kind of comes along with that. Okay, so let's do another problem real fast. Just check my notes here, make sure I get that right. Okay, so let's go through here. Let's do, just did 72, I don't know, 76. Let's go to the very last section now so I can get a problem out of there. Okay, let's do 292. This comes out of the last section where they talk about the dot product. 292. Okay, so we have in this right-hand coordinate system, there's I don't know, some type of wooden stake here sticking about at the ground. And there, I guess there's two forces coming out of it. Looks like this direction, and another one's going over here. Okay, so these pictures, you really have to be kind of careful with what you're looking at and what's being said. So it tells us this right here is one. It tells us this is from here to here. It's 2. Try to write this as neat as possible. It tells us this height here says this height here is 3. And it also tells us this distance here is 0.75. Okay, supposed to be a decimal there. There it is. So 0.75 is that distance there, and then over here is 1. So it's like it's kind of coming out a little bit. And let's see, what else did it give us? It tells us this angle on the bottom here this angle here is 40. And the hypotenuse of that angle on the XY axis there is 2. Okay. So that was just getting the picture out. So let's call this point up here A, this point down here C, this point down here B. There's two forces pointing outwards, I guess, right? This force is force AC. This force over here is force AB, right? Okay. Force AC is 400. And force AB is 250. All right. Okay, so there's the picture. Now we're looking at 292. All right. The question asks, express each force in Cartesian vector form and determine the magnitude and coordinate direction angles of the resultant force. Okay, so we want to write F1 and F2 in like vectors. We want to write them in terms of vectors, but they give us the magnitudes. And determine the magnitude. Oh, it's right over here. Find force AC vector and find force AB vector and find the magnitude of the resultant force and directional angles of it. Okay, I don't know if I have enough time to find all of that, but let's see how far I can get in the next 15 minutes. Okay, so first, in the previous section, we talked about position vectors, and we talked about how we can write a vector in terms of its position vector, but it's more like a unit vector. But we write the unit vector using position vectors. So let me write out what I mean here. So basically, we know we can write this. We can write out force as its magnitude times the unit vector u. Right? So this u, this unit vector u, is equal to the position vector divided by the magnitude of that position vector. Okay, that's all it is. So basically, we want to find the two position vectors or the two unit vectors that look like this. So we want to find the UAC. We want to find the AB. Excuse me. So that's going to be RAC, magnitude. Similarly, oh, wait a minute. It's supposed to be B, right? Yeah, AB. Actually, catching that. There we go. So we're going to solve for both of these. Once we solve for both of these, we can just basically multiply it by the forces here, by these forces, and then they give us these vectors. So we could say, okay, force AC is going to be the magnitude AC times U AC. Boom, boom, and AB. All right, okay. So how do we find, let's go to where the root of it here, AC, RAC, and RAB. Okay. So this position vector is basically the final position minus the initial position. The final position, so C minus the position of A. So let's write out where each one of those positions are. Right here, A is located it has 3 points. Starting with the x, A is located to 0 for the x, right? Looking at point A here, it's along the line, so it's at 0, 0, comma, looking at the y now. Set a negative point in the y, because it's along here is the y, it's going downwards, negative 0.75, negative 0.75, and the z is how high up it is. Well, that's 3, so 3. And that's the A position. Let's do the C position. Over here, starting with x, it goes out this way by 2, right? 2, comma, let's look at the y now. Well, it has no y because it's, well, actually does have a y. It's negative 1. Goes back that way. And z, it has no z. That's what I was thinking. There we go. And so lastly, the b is over here, which we have to analyze a little differently. Because they gave us the angle here. This angle is 40. That angle is 40. They gave us the hypotenuse, which is 2. So the x component is going to be the cosine, right? So let's write that out. The x component is going to be 2 cosine 40. And so the y component must be 2 sine 40. And let's see, finally the z, well, it's on the ground, so the z is 0. All right. Okay, so that was just the beginning there. That's going to help us, this is going to help us find our RA and RC. All right, so it's going to be the final position minus the initial position. So it's going to be pointer. So for RAC, it's going to be, let me just change colors here. RAC, like this. Right? So at the final position, so the final position C, so C minus A, so 2 minus 0, negative 1 minus, let's make that a plus 0.75, that's supposed to be 0.75 there, that's what this is. Oh no, I forgot to include this guy. Oh wait, no, I did. 0. So we're looking at y, right? 0. I forgot this guy right here, actually. Oh, I gotta erase some of this. Okay, that was an accident. Okay, well, let me just pick up back up with writing RA and RC, right? Hopefully you kind of got all that. RA and RB. So basically I got this, I'm writing it all out. And that was J, this is K, this is I. Okay, again, this is coming from subtracting C from A, so now I'm going to subtract B from A, and when I do that, it looks like this. Got 2 cosine of 40 minus 0, that's the I hat, plus 2 sine 40, right, minus plus 0.75, close parenthesis in, right, J, plus, finally, what do I have here? It's like 0 minus 3. Okay. Okay, so now we have that, so we can actually solve for the magnitudes of both of those, right? And we need the magnitude because we're trying to write the unit vector. So again, we're trying to write these unit vectors UAC. So I'm just going to do one of them here. RC magnitude. So on the top, looking at RC, that's 2I. Is that minus? That's right, that's minus 0.25. And that's 30. Divided by the square root, so it's each one of those squared. Okay. So once we have each one of those squared, we basically then have our unit vector for AC. And then we can immediately jump to writing this. Well, force AC is equal to the magnitude of AC, which is 400, times this. Right? And that works out. It makes sense because this is a vector and force AC is a vector, so multiplying by this magnitude gives us another vector. And kind of notice here we have this this I, J, K component. Okay, and we basically do the same thing for the other one, right? A and B. Okay, so we can solve for basically A or F. These two forces, right? Real fast. Okay, so the resultant force then that's what we want to solve for. It's 400 UAC plus 250 UAB. All right, boom. So then we can solve for the resultant force, right? It's kind of speeding up here. So once you solve for UAB and UAC, which you saw how to do that using the position vectors and dividing by the magnitudes, we can take each one of those multiplied by the magnitudes of AC and AB that they gave us here for 400 and 250. Then we just add up those two vectors by adding up their components, right? Now to give us the resultant. And then finally, we can find the magnitude of the resultant, of course, which is just going to be the square root of the x component plus the y component plus this e component. Okay, so that would get you to the magnitude of the force. And I think the last thing they wanted you to solve for was these directional angles. actually do, because I know all of this here. FR magnitude, right? And so on for the last one. So we can solve for alpha because we know this, we know the x component of the resultant, which is right here, which you solve for by adding these two, right? The x component of both of those. Okay. Yeah, and then that would be how you solve problems. This is 92. Okay, well, that's about it for today. This is pretty much how I'm gonna be doing this weekly. Uh, this is my first time, so as the weeks go on, hopefully I'll be like more organized and whatnot, and have like maybe better examples if you didn't like the examples I did, or if I can either slow up or slow down, do more examples, less examples, anything like that. Just let me know. All right, see you next week.